Today we shall discuss two quantum phenomena, and these are the photoelectric effect and the Compton effect. Let us first discuss about the photoelectric effect. Okay, let us consider an evacuated tube, and we have a metal surface here, and these are two electrodes, and they are connected to a battery here. Okay, this one is C, cathode, and this one is A, anode. Now, if light with appropriate frequency falls on the metal surface, then electrons will be ejected from the metal surface. And the electrons will be attracted by the anode. You see, we have connected the positive terminal of the battery to this electrode A, and the negative terminal of the battery is connected to this metal surface. So compared to C, A is positive. So when the electrons are emitted from the metal surface, they will be accelerated towards the anode A. The light, and we know the energy of light. If we consider photons of light, then each photon has energy hf. F is the frequency of the light. And this phenomenon, when light falls on metal surface and electrons are emitted, and this phenomenon is known as the photoelectric effect, because these photoelectrons, though the electrons that are emitted from the metal surface, they can generate electric current through this circuit, and the current generated is known as the photocurrent, and the electrons are photoelectrons. And this is a galvanometer, or you can insert an ammeter to measure the current. Now we shall discuss two experiments concerning to this photoelectric effect. One is this. If we plot along the x direction, if we plot the applied voltage, that means the applied potential, and along this direction, if we apply the photo current, a potential, is a photocurrent. Now then we shall see that the behavior of the photocurrent will be like this. For positive voltage or positive potential that is applied to the two electrodes, say when this A is positive, and this C is negative, then we say this is positive potential applied. And in that situation, we see the behavior of the photocurrent is constant with respect to the applied potential. But if we reverse the polarity of the battery, so if we connect the positive this side and the negative is this side, then this electrode will be negative compared to this. So the electrons will be retarded, and this electrode will then repel the electrons, and so the current will decrease in the circuit. And that situation can be explained by the help of this figure. This V naught is the particular negative voltage. At this voltage the photocurrent becomes zero, and this voltage is known as stopping, or this potential is known as stopping potential. We have drawn here two curves. This is for comparatively higher intensity, high intensity of light that is falling on the metal surface, and say low intensity, this one. So one observation is, if we increase the intensity of the applied, the light, this light, okay, if we increase the intensity, then the photocurrent also increases. Okay, second observation, and that is if we want to discuss by the help of a figure. Along the x direction, we plot the frequency of the light falling on the metal surface, and along the y direction we plot the kinetic energy of the photoelectrons, maximum kinetic energy of the photoelectrons, and frequency, and say kinetic energy of the photoelectrons. And we shall see that the behavior of the kinetic energy will be like this, and at a particular frequency we call it f naught. Okay, this is known as the threshold frequency. So below this frequency of light falling on the metal surface, no electrons will be ejected, and so you see there is zero kinetic energy. There is no electrons ejected. If you increase the frequency from this f naught, then you see the kinetic energy of the photoelectron increases linearly. So these are the observations that we get from the photoelectric effect experiments. This photoelectric effect is a completely quantum effect. One observation is that when the light falls on this metal surface, as we have seen that there should be a minimum frequency for each type of metals. This threshold frequency changes with different metals. This is known as threshold frequency. Threshold. And this threshold frequency is different for different metals. Different for different metals. There is no time lag between the falling of light on the metal surface and the ejection of electrons from the metal surface, and this can happen only if the phenomenon is considered to be purely quantum mechanical and not classical. This effect is quantum because when light falls on the metal surface, and we know light consists of discrete photons. Photons are energy packets, and they are like they behave like particles, virtual particles. So when photons, they strike the electrons on the outermost shells of the atoms of the metal surface, then there is interaction between the photons and the electrons, and energy will be transferred from photons to the electrons. Also momentum will also be transferred, and the energy of each photon will go to liberate the electrons from the metal surface, and the rest of the energy will be used to accelerate the metal surface. That means that will be kinetic. So if we consider that h nu is the energy of a photon, or hf the energy of a photon, and phi, a quantity known as the work function, and T max is the maximum kinetic energy of the photoelectron. Then okay, and maximum kinetic energy can be written as 1/2 mv max. Then according to conservation of energy, we can write down h nu, I'm sorry, hf. This is phi plus T max, or work function plus kinetic energy of the photoelectron. So m is the mass of electron. So this equation actually is the conservation of energy, and you have to solve problems later on at the end of this um, chapter by using this formula. Classical mechanics is unable to explain this phenomenon of photoelectric effect. Classical mechanics, or classical physics actually, okay, let us then now discuss another quantum effect, is the Compton effect. Here, let us suppose that we have an electron here, and we have two perpendicular axes. This is, let us say, x-axis, this is y-axis, and we have an electron here, and a photon of light is approaching towards the electron. For simplicity of presentation, we consider that the electron is at rest, or electron is free electron. A photon with energy hf and linear momentum hf by c. This a photon is approaching towards the electron, and after the collision with the electron, the photon starts to move along this direction, and the electron will move along the another direction, say suppose along this direction. And let us suppose that the theta is the angle between the scattered photon and the original direction of movement of the photon. This is say hf prime, the new frequency f prime of the scattered photon, and the linear momentum is hf prime by c. And here the energy of the electron is the rest energy m naught c square, and the linear momentum is 0. And after the let's say this angle is phi. So after the collision, the electron will move with the velocity, so the energy will be mc square, and the linear momentum is supposed p. Okay, this phenomenon, when a photon of light strikes an electron, and there will be transfer of energy and linear momentum from the photon to the electron, and the electron will gain energy and will starts to move, making along a direction, making an angle phi with the original direction of the photon, and the photon will be scattered along a direction, making an angle theta with the original direction of movement of the photon. Now after collision, the photon will lose energy, so the energy will be hf prime will be smaller than hf. That means f prime is smaller than f. F prime is the frequency after scattering. Okay, this phenomenon is known as Compton effect. When the photon strikes an electron, there will be a collision, there will be a exchange of energy and momentum, and the photon will be scattered along a direction, and electron will be moving along another direction, and this phenomenon is known as Compton effect. For simplicity of presentation, we shall consider that this happening on a two-dimensional plane. So we have drawn here two-dimensional plane, OX and OY, two axes. Now we are interested to find the change in wavelength of the photon. Because before collision, the wavelength is a lambda, which we know will be given by speed of light divided by the frequency, and after collision, the wavelength will be lambda prime, which is c divided by f prime. Since f prime is smaller than f, therefore lambda prime will be greater than lambda. So we can find the change in wavelength. We are interested to find the change in wavelength of the photon. And we shall see that delta lambda, which is the difference in lambda, so is lambda prime minus lambda, will be given by this h Planck's constant divided by m naught c. M naught is the rest mass of the electron, c the speed of light, and then 1 minus cos theta. So we are going to prove this going to derive this relation, change in wavelength of the photon due to Compton effect. To derive this relation, we'll have to apply a conservation of energy and conservation of momentum. We need to consider the conservation of energy and momentum, conservation of momentum. Linear momentum. And we have this system consists of two particles. One is the actual particle electron, and the other is the virtual particle, the photon. Now, if we apply the conservation of energy of the system, so we'll have to equate the total energy of the system before collision or scattering and total energy of the system after scattering. The energy conservation. So the electron, so the photon has energy HF and the electron has energy m0 c square before collision, and after collision the energy of the photon is HF prime and the energy of the electron is mc square. Okay, so this is one conservation relation, and other the conservation of momentum. There will be two equations for the conservation of momentum, because momentum is a vector quantity, so it will have two components along the x direction and along the y direction for two-dimensional case. So along x direction, the linear momentum of the photon is hf by c, and there is no motion of the electron, so it is 0. And after collision, the linear momentum of the photon will be hf prime by c, and there will be a factor cos theta. You see, theta is the angle made by the scattered photon with the x direction. So along this direction, the component of this will be hf prime by c into cos theta along this. Okay, so we are taking along x direction, and another component after collision, the component of the linear momentum of the electron. So, and this is m into v. So instead of p, actually we can write down this mv. M into v. Of course, m will have to apply the relativistic m. This is 1 minus p square by c square. So we'll have to use this. Okay, so let us first and this one will be mv sine phi. So if we write down in terms of m naught, this m, so h f prime by c cos theta plus m naught v sin phi by square root of 1 minus b square by c square. Okay, so this relation we have along the x direction, the conservation of linear momentum. Now along the y direction, so along y direction, so y direction, the linear momentum of the photon is 0 because the photon is moving along the x direction, so 0, and the electron is stationary, so 0, and the linear momentum of the photon along the y direction is hf prime by c sin theta, and this one will be mv. Okay, I'm sorry, this actually will be this one will be cos, because we are taking the component along x direction, so this is not sine, this is cos. You see, we are taking the component along the x direction, along this direction, so this m will have component along this direction is will be cos phi factor here. Now we will have sin phi and hf prime by c sin theta, and this is m naught v sin phi divided by square root of 1 minus v square by c square. So this is the conservation of momentum along the y direction. So now we can apply these three relations, this one, and this one. First we eliminate phi, second eliminate v, okay, and the ultimately we will be forced into get this relation. The detail of the derivation is in the note, I mean the PDF that has been uploaded in the Google Classroom, so you can study the notes and you will find that ultimately we will get okay, we'll divide by f prime, so this one will be 1 by f prime and this one will be 1 by F, and we'll have H divided by m naught c square 1 minus cos theta. Okay, now if you multiply by c both sides, then we'll have c by f prime minus c by f, and this is h divided by m naught c, and will be 1 minus cos theta. And c by f prime means lambda prime, and this is lambda. You see, you can then find this, and this is delta lambda. Okay, so this is another formula. We can use this formula to calculate the change in wavelength of a photon due to Compton effect. As I mentioned, that if you study the notes that I have uploaded in the Google Classroom, the derivation is there, the complete derivation, and things will be much easier for you to understand. Okay, this is for today. In the next lecture, we shall discuss about the de Broglie hypothesis and the wave particle duality.